area of regions bounded by curves in polar coordinate system. In the previous video, I showed to you a few curves that appear in the polar coordinate system. Now, before I go into using the integral to get the area of regions bounded by curves in the polar coordinate system, let us go back to how we did it in the rectangular coordinate system. So let's say, for example, we are interested with what is the area of this shaded region bounded above by a continuous function, bounded below by the horizontal axis from A to B. So the area of that region is equal to this. It is equal to the integral of f of x dx from A to B. But before we were able to get there, this is actually what we did. We produced a partition of that interval. And in that interval, we constructed these rectangles, a finite quantity of rectangles. And then we get the area of each rectangle, the sum of all those areas. The sum of the areas of all the rectangles is going to be an approximate of the area of this bounded region. Now, if we want to get close to the true area, we must produce an infinite quantity of rectangles. And so the area of that sum is going to be this, the limit of the sum of f of x times delta x. Each of that is just the area of a rectangle. There is another part here that I chose not to talk about because you are computer science students. I also don't talk about that even when I am teaching to engineering students. But since this is a recorded lesson, I don't have to do this every time I teach integral calculus in a normal classroom setting. Since this is a recorded lesson, I might just as well talk about the other part of getting the limit. Because you know that the limit of functions don't always exist. You saw that from differential calculus. So in order for us to be sure if the limit of this sum indeed exists, we must do two sums, okay? The first summing is what we call the lower sum. We are inscribing rectangles into that region. The other summing up is what we call the upper sum. What we will do is we will circumscribe that region with rectangles. And so you can see here the differences. In the lower sum, all our rectangles are contained inside the region. But in the upper sum, okay, there is a small part of our rectangles that is outside the bounded region. Now, as n approaches infinity, if these two sums converge to the same value, then we are sure that the limit exists, and also the integral of f of x dx from A to B also exists. Now, let us do it for regions that are bounded by curves in the polar coordinate system. So let us say, for example, we are interested in getting the area of that region, the red region. So it's bounded by a curve. It's bounded by a curve. That curve is actually defined by this equation. R is equal to 3 times cosine of theta. And the radial interval, okay? So that is how we say it. The radial interval is from 0 to be there. The theta there is actually equal to pi over 3. Okay, what shall I do? What must we do? Okay, so we can do something that is similar to what we did in the rectangular coordinate system. We will produce a partition of the radial interval. Okay, we will inscribe as many sectors of a circle as we can inside that region, and we will get the area of each of those smaller regions. And how do you get the area of that small region? Well, the geometric object that will help us get the area of those thinner regions will come from the circle. So in the rectangular coordinate system, we used rectangles. Here, we are going to use the sector of a circle. Okay? So let's say, for example, we want to know what is the area of that red region. So what I will do is I will subdivide this into smaller sectors. Smaller sectors. And how do you get the area of a sector of a circle? You get it this way. A sub I is equal to 1/2 times r squared times delta, or the change in angle, or the size of the central angle. But this is for one sector of a circle. Now, if you want to approximate, if you want to produce a better approximation of the area of that sector, this is what you do. For an n quantity of sectors, the approximate area of that region is going to be this. It's the sum of 1/2 times r sub I squared times the change in angle. Okay, so look at this. I'm using r sub I, okay, not simply r. Okay, so you might be thinking, hey, isn't it that the radius of a circle is the same, r? But we are talking about curves in the polar coordinate system. They are not always circles, okay? So that's why I will use that notation instead. It's the square of r sub I, okay? And then 1/2, of course, is a constant. You can factor out 1/2. So the true area must be the limit of that sum as n approaches infinity. And if the limit exists, that is what we call the area of that bounded region using the integral. So the area of that bounded region is going to be 1/2 times r squared times delta theta, okay? Evaluated from alpha to beta. So alpha and beta, they define the radial interval of your function. So it's different, okay? Well, they are comparable. Okay, so how we develop the definite integral in the rectangular coordinate system is comparable to how we develop it in the polar coordinate system. Okay, so let us go back to this region. So this region is, but the curve is defined by this equation. R is equal to 3 cosine theta. And we will get the area of that region, the red region. And so that region is contained in the radial interval 0 to pi over 3. Let us now set up the definite integral. A is equal to 1/2 times the integral of 9 times the square of cosine theta d theta. Why 9? Why did it become the square of cosine? Because that is how we are computing it. Okay, so let us go back to the earlier slide. This is how we compute it. Okay, A is equal to 1/2 times the integral of the square of r times d theta. Okay, I think that should be d theta. I'm sorry. Okay, so this is how we put it. Okay, and 9 is a constant. We can factor it out. And the square of cosine of theta d theta. Again, this will bring us back to our earlier lessons. Okay, we will use your power reduction formula. The square of cosine theta is equal to this, 1 plus cosine of 2 theta all over 2. This is equal to 9 over 2 times this one. So this is the antiderivative of 1 plus cosine of 2 theta over 2. And that must be evaluated from 0 to pi over 3. I know that this is a lot to do. I will not require you to do the integration completely, okay? I will not require you to do that. If we shall evaluate this from 0 to pi over 3, okay, the area of this region is equal to this. 3 pi over 4 plus 9 times square root of 3 over 16 square units.